Hello, everyone, and welcome to this lecture in the Hands on Large Language Model series. Today, we are going to continue looking at text classification, but we are going to learn about one more way to solve the problem of text classification using large language models, and that is through the use of embeddings. In the previous lecture, we started looking at how representation models can be used to solve the text classification problem. We had the movie review data set, and the goal was to look at a movie review and to classify whether it's a positive review and or whether it's a negative review. We saw that using representation models, there are two ways of achieving this task. One way is to use a pre-trained model which is already fine-tuned on a specific data set. That's the first route over here, which we explored in the previous lecture. We achieved an accuracy of zero point 0.8 and an F1 score of also close to zero point 0.8. Yesterday, I also told you that there is one more method in which you can use representation models such as BERT as your base model, and then you can do something called an embedding. You can develop something called as an embedding model, which also can be used to predict the sentiment of the movie reviews. So today we are going to learn about what do I mean by embedding model and how embedding models can essentially be used to solve the text classification problem. First, let's start with the motivation. Why do we even need to consider embedding models in the first place? Well, there might be two reasons. First, you remember in yesterday's lecture, we looked at a pre trained model which was fine tuned on a specific task, and that specific task was Twitter data. So the model which we looked at in the previous lecture was fine-tuned on Twitter data, I think around 124 million tweets. And then we used that pre-trained plus already fine-tuned model on the movie reviews. But the problem is, what if we cannot find a pre-trained model for the task? Luckily, in the previous lecture, the pre-trained model, which was fine-tuned on a completely different data set, worked on our movie reviews data set. But what if we cannot find a pre-trained model which works for a specific task? This can be one issue. The second issue is that, okay, if we cannot find a model which is fine-tuned, what if we do the fine-tuning ourselves? But even then, fine-tuning takes a lot of compute power. So if we don't want to do the fine tuning ourselves, or if we don't have the compute power to do the fine tuning ourselves, then essentially going the first route is not the best way to achieve the text classification or to complete the text classification task. And that's why we have to look at the second route over here, which is essentially to create an embedding model. When you work with embedding models, you don't have to fine tune the model. It's a completely new way of doing the text classification. In particular, the embedding model works in two stages. First, what we do is that we have the data set, right? And the data set essentially consists of, let me write it over here. Actually, let me write it over here. The data set consists of movies, and we have a review. That's one document. That document number one. Similarly, there are document number two, and I think we have around 5,000 such reviews. What's done in the embedding model is that first, each of this document is converted into something which is called as an embedding. What is an embedding? The simplest way to think of an embedding is that it's a vector in a higher dimensional space. So here I am showing a vector in a two-dimensional space, right? Usually, each document is converted into an embedding, let's say of 500 or 768 dimensional vector. So if we have 5,000 movies, every document is converted into a 768 dimensional vector. Now, these embeddings are not random vectors. These embeddings have also been pre-trained so that they capture something about the data set. They capture meaning, they capture semantic relationships between different sentences. So the embeddings which are already given to us, in this case we are going to use pre-trained embeddings. They have been trained on data set and they do capture a lot of meaning about the text and the sentences. That's how these embeddings are constructed. To create the embeddings from the documents, that itself takes pre-training and that takes compute power, but we are going to use pre-trained embeddings already, right? So that's the first step, and that's called as feature extraction. In the feature extraction step, we take the documents and convert the documents into embeddings. Okay. And the second step is called as classifier. So in the second step, we pair the features which are extracted with a traditional classification algorithm such as logistic regression. You can even add a neural network layer for classification. So then the vectors, the each of these 768 dimensional vectors are then passed into a traditional classifier such as logistic regression, and then we have the prediction whether it's a positive review or whether it's a negative review. Do you see the advantage of this method compared to fine tuning? The second part, which is the classification part, can be trained on a CPU because it's a much simpler and a more traditional model to train. For the first part, we'll just use a pre trained embedding model. So we don't have to expend any computational power for this part. These are the two steps which are involved in the embedding model, and that's why it's called as the two-step process. Now, here I have just zoomed into this part where the second part is the classifier. So, what happens is that, let's say if we have a higher dimensional vector, let's say at this stage we have a 768 dimensional vector, that's passed as an input to this logistic regression. The logistic regression model is trainable. So, here the parameters are trained, but those are not too many parameters. So, that training can be done on the CPU itself, and then we predict either 0 or 1. So 0 for a negative sentiment and 1 for a positive sentiment. And here I have zoomed onto the embedding model itself. So we are going to use a frozen pre-trained embedding model. So we are not going to train this again. We are going to use an already pre-trained embedding model so that this process does not take any compute power for us. That's the action plan which we are going to implement in today's lecture. So now let me get started with the practical implementation of how exactly are we going to do this in code. So the first thing we need to do is that we need to find an embedding model. What's the embedding model which we are going to use, which will take my document and convert it into that 768 dimensional vector? The embedding model which I'm going to use is called as the sentence transformer. So, Sentence Transformers is a Python framework for state of the art sentence, text, and image embeddings. You'll find it on Hugging Face. It's a library provided through Hugging Face. Now, when you use Sentence Transformer, you also have to give an actual model which we are going to use. And there are several models within Sentence Transformer. In this code, we are going to use the all MPNet base version 2 model. What this model does is that it maps sentences and paragraphs to a 768 dimensional dense vector space and can be used for tasks like clustering or semantic search. This you can see that the intended use cases, given all an input text, it outputs a vector which captures the semantic information. So it's already pre-trained, and you can even check the pre-training procedure which they have used. I think it's a pre-trained model given by Microsoft, and it's a very popular model. They have even mentioned about the pre-training data, what they used for pre-training, time taken for pre-training, etc. So you can take a look at that, and you can also look at the number of downloads last month. So just last month itself, this model had I think around 100 million downloads here. So which means it's pretty popular, and we can definitely use this model. So here you can see that the vectors, when this model takes in sentences and converts it into vectors, it retains the meaning between those sentences. So if the source sentence is that is a happy person, you can see that this sentence is comparable to that is a happy dog, that is a very happy person, today is a very sunny day. So you can see that there is a positive or an optimistic emotion which is retained in all of these sentences. That's why these sentences are closer to each other. So imagine a 768 dimensional vector and another 768 dimensional vector being close to it in vectorial space. That's what I mean mathematically when I say that two vectors are more related to each other. The distance metric, whichever distance metric which we are going to use, that's shorter for vectors which have semantic meaning similar to each other. So all of these vectors here, that is a happy person, that is a happy dog, that is a very happy person, today is a sunny day, will be vectors which have short distances between them, short vectorial distances between them. That's the power of this all MPNet base version 2 model. It's a sentence transformer, which means it maps sentences into vectorial embedding space or into vector embeddings. And these vector embeddings are not random, they capture meaning. So we are going to use this as our embedding model, and then we are going to connect it to a logistic regression framework in the second step. Okay, so now let's jump into code. Here, let us first let me show you this code. This code, as I've told you before, I'm following this book, Hands-on Large Language Models by J. Alamar. This book came out last month, and it's pretty awesome for project-based large language model learning. The first thing you have to do is that you have to install the necessary libraries. You have to install the datasets package from Hugging Face. You have to install transformers, sentence transformers, and OpenAI as well. Today we'll just need datasets, transformers, and sentence transformers. So when you click on this install button, these packages will be installed, and then you'll be ready to go. The second thing which you need to do is that you need to load the dataset. So we are going to be using the Rotten Tomatoes dataset from Hugging Face. So you can just search Rotten Tomatoes Hugging Face, and you will see that here's the dataset. We basically have movie reviews, and you will see that the training data has 8,500 rows, the validation has around 1,000 rows, and the testing has 1,000 rows. So overall, we have around 10,000 movies split into 85% validation, uh, and the remaining into training, and the remaining into 85% training, and the remaining into testing and validation, roughly. And we have to take these movie reviews and we have to classify them into either a positive sentiment or a negative sentiment. All right. So when you load this data set, you can print out the data and check whether it's loaded correctly. You'll see that the training we have 8530 movies. In the validation we have 1066 movies, and in the testing we have 1066 movies. That's exactly what we saw over here, which means that the data set has been loaded correctly into the Google Colab notebook, right? Okay. Now we can move next to uh, the specific code which we are going to run today, and that is the supervised classification. The reason it's called supervised classification is that we are following this two-step procedure in which we are using embedding with classifiers, and there are labels also here, so we know what is a correct answer and what's the wrong answer in the training data set. That's why it's called as the supervised classification. Okay, so the first thing to do is that we have to load the sentence transformer itself, and we have to pass the exact model which we are going to use. And the exact model, as I told you, is this sentence transformer slash all mpnet base version 2. So that's what I'm doing here. I'm calling the sentence transformer module from Hugging Face, and I'm passing the exact model which I have to use. And then to take the documents and convert them into vector embeddings, what you have to do is that you have to do model.encode. So what model.encode will do is that it will take the data, it will go to first the training data and access the field called text, which are the reviews, and then it will convert each review into a 768 dimensional vector embedding. So we have the training embeddings over here and we have the testing embeddings over here. If you print the training embeddings.shape, you will get that there are 8530 movies, and for each movie now we have a 768 dimensional vector. So the training dimension shape is 8530 comma 768. If you print the testing dimension, test embedding dimensions, you will get, so let me try doing this. You will get 1066, I think, or how many testing data we have? 10, yeah, 1066 comma 768. So you can just do these checks to see whether first of all your understanding is correct, and secondly whether the vectors have been constructed correctly, right? So the first part of this two-step procedure is done. We have done the feature extraction, we have taken the documents and converted them into a 768 dimensional vector. Now we have to implement the second part, which is the logistic regression module. So here from scikit-learn, we are importing logistic regression. You can go to scikit-learn and type logistic regression. It's one of the most widely used models in the scikit-learn framework. So we are using this logistic regression module, and we have to use the clf.fit. So we initialize the logistic regression CLF and then use clf.fit. And in this, we have passed the train embeddings, which means the vector embeddings for the training data. And we have passed in the labels also. Remember, this is a supervised learning. So we have to know what's the correct answer for each data which we have. And then that's it. To predict the performance, we do clf.predict. That's the simplest way to use logistic regression. You define the CLF, which is the logistic regression module, and then you do clf.fit to train the logistic regression, and then you do clf.predict. Then you will have the prediction for each of the testing data. So in clf.predict you don't give train embeddings here, but you give test embeddings, because the performance on the test embeddings is what really matters to us. And then you evaluate the performance. So as we saw in the previous lecture, the performance is evaluated based on the following metrics: accuracy, F1 score, precision, and recall. So first, I want you to check the accuracy. It's 0.85, which means that 85% of the time we are correct. Now, if we compare this accuracy to the accuracy which we got when we did the fine tuning uh, approach in the previous lecture, we can see that the accuracy which we get right now using the embedding model is much higher. In the F1 score, the previous F1 score we got was 0.81 for the negative review and 0.78 for the positive review. But now, using the embedding model, we have got an F1 score which is equal for both the categories. That's awesome. Remember what I mentioned to you last time: the F1 score higher than zero point 0.8 is good, and generally, the F1 score for the negative review class and the positive review class should be close to each other. And here, not only is the F1 score higher than the previous fine tuning case, but the F1 score for the negative review and positive review are also closer to each other. Similarly, if you take the precision and recall, we have 0.85, 0.86, which is much higher than the precision and the recall value generally which we got in the fine tuning case. So this is awesome, right? Just by using an embedding model which was already pre-trained, we could get a classification. We could get a classification accuracy which is 85%. We could get an F1 score which is 85%. So I just want to show you here the power of the sentence transformers. When you take a sentence and convert it into vector embeddings, that vector embeddings really captures the semantic meaning. And that's what is being used in the logistic regression later. So if the sentence transformer was random, the logistic regression would have a very hard time to train on the data and predict as well on the testing data. But now, because the meaning is already captured through the sentence transformer, the task becomes much more easier. All right. So now what we can do is that the second case which I want to consider is, what if we did not have labels? So currently I've shown you this example where we had this movie data set, right? And in the training data there was a label. So we had already looked at each of the reviews and we had classified them as a positive review or a negative review. So the training data had labels, but we won't have this luxury every single time when we deal with data sets, right? So what if we have no labels? Can you think of what we can do in this case? So I'll tell you what we have. We just have a bunch of reviews. That's it. And the task is just using a bunch of reviews. Can you construct a system so that when I give you any new review, you can classify it to be positive or negative? Of course, the first way is that you will say that I will sit down for a huge amount of time and I will label it manually. But again, it takes a lot of time. Is there any other way? So you can pause the video here for now and try to think about how can you do this classification without labels. All right, so let me reveal the answer right now. There is a very creative way to do this. Although you don't know which movies are positive and which movies are negative, right? What you can do is that you can construct a sentence, let's say a positive movie review, and you can construct a sentence, let's say, called a negative review, a negative movie review, and then you can obtain the vector embeddings for these two sentences. So here's the vector embedding, the green for the positive movie review sentence, and the red is the vector embedding for a negative movie review sentence. So let's say these are the two vectors. Then all you need to do is that when you are given a new movie, such as let's say the movie is best movie ever, you take this vector and you check the cosine similarity between the other vectors. So cosine similarity is just the cosine of the angle between the vectors, right? So here you can see that this is now more closer to a positive movie review because the angle is lower. So cosine of theta 1 will be greater than cosine of theta 2. So that is why we'll say that this review is more likely to be a positive review. Whereas if for some other movie the vector lies here or the vector lies here, we'll see that that movie has a lesser angle with this negative movie review vector. and that's why the cosine similarity with the negative movie review will be higher, and that's why we'll say that this particular movie will have a is more likely to be negative. Do you see the how we leverage the sentence transformer here? Sentence transformer encodes meaning, right? So what we did was we took this one sentence, a positive movie review, and we took one sentence, a negative movie review, and we projected them into the 768 dimensional vector space. Then what we did is, when you get any new vector, all you need to do is you need to check whether it's more closer uh, to this positive movie review vector or whether it's more closer to the negative movie review vector. Then you calculate the cosine similarity. So the cosine similarity between best movie ever and a positive review is 0.92, whereas the cosine similarity between best movie ever and negative movie review is 0.08. And then you choose the one which has a higher cosine similarity. So in this case, the best movie review is more likely to be a positive review. Isn't that awesome? This also comes under the category of zero shot classification. In zero shot classification, the idea is that you don't annotate data with labels. You know what the labels are, you just know the category of labels. Let's say if you have this sentence, you know the category of labels, but you have not pre-trained any data with these categories. In zero shot models, you just take the input and then you have to predict unseen labels. So we don't have any label data, only the labels themselves. That's the zero shot model. So in this case, what we are doing is that this whole framework of these three images, what you're seeing on the screen right now, image number one, image number two, and image number three, we don't have any labels for the training data. We have constructed a framework which is zero shot classification. We just know that there are two types of labels, there is a negative and a positive, and we have constructed a very smart framework to leverage the vector embeddings and the fact that sentence transformers capture semantic meaning to classify new movies as having a positive review or a negative review. That's why we are also calling this an example of zero shot classification. Awesome. Now let's go ahead and implement this in code. So what I'm going to do, as I mentioned, is that I'm going to take two sentences, a negative review and a positive review, and I'm going to convert them into vectors. So I'm going to do model.encode and a negative review and a positive review. So this will generate two vectors in the 768 dimensional space, the green vector and the red vector. So let me rub some things over here. Yeah, the green vector and the red vector. That's the first step. Then what I will do is that I will just find the cosine similarity between my all the test vectors and my label embeddings. That's it. It's as simple as that. Whenever you get a new vector from the testing data, such as this vector, you just find the cosine similarity between this new vector and both of these vectors, and then you choose the label with the higher cosine similarity. So then what we are doing is that we go through all the test embeddings and then we find the cosine similarity between each test embedding and the label embedding. And then the predicted label will be the that uh, index or that either positive or negative which has a higher cosine similarity. So in this case, if the cosine similarity with the negative review is 0.08 and with the positive review it's 0.92, the answer will be a positive. It will be a positive review because it's the cosine similarity is higher for this positive review class and it's lower for this negative review. So we just do np.argmax similarity matrix and x is equal to 1. And then again we plot the evaluation matrix as we plotted earlier, and here you see that the f1 score has dropped a bit. The f1 score for positive and negative has dropped a bit, the accuracy has also dropped a bit, but it's still not bad at all, right? We have almost got an accuracy of zero point 0.8, which means we are 80% correct without even having the labels at all. I find this incredible because here we have clearly leveraged that text has meaning and sentences have meaning which images don't have. So that's why here we have truly leveraged the power of text. Instead of manually labeling as positive negative positive negative, we constructed vectors, and then we saw out of each test data it lies closer to which of the vector, whether it lies closer to the positive movie review vector or whether it lies closer to the negative movie review vector. I thought it's very creative and it really leveraged or used the power that sentences are not random, right? There is meaning. If a movie review is positive, it is more likely to be closer to the vector for a positive movie review, and that's what we have really used here. uh, okay, so this brings us to the end of this lecture, where again we have seen a second way to use representation models for text classification. The first way was to use fine tuning, and the second way is to take the base representation model, convert it into an embedding model, and then add it with a traditional ML model such as a classifier or logistic regression, which can be trained on CPU. And then we also saw how we can use the embedding model if even if we don't have labels. That's what makes this embedding method so powerful. I hope you're liking these lectures and you're liking this whiteboard approach plus the coding approach. In the next lecture, what we'll do is that we will look at how generative models can be used for text classification. Until now, we looked at two categories of representation models, right? Fine tuning and the embedding. But in the next lecture, we'll be looking at how generative models can be used for the fine tuning task. Sorry, how generative models can be used for the text classification task. So thank you so much, everyone, and I look forward to seeing you in the next lecture.